it comes to precision in agriculture, many people would think of a massive tractor that costs up to $1 million. But where does the real question lie? The real question lies in what does your soil actually need and how much resources does it need? My name is Tan Ru, the project manager of Group 5 of the subject instrumentation. And right now, commercial farming is facing a lot of challenges, including the water resources crisis. Many farm owners are pouring over 1 million gallons of water into their fields purely by guessing rather than following a specific framework. And to do manual testing on how much water resources they need, that is almost impossible at such large scale of a farm. And human error, that is unfortunately guaranteed. That's why the Group 5 has come up with a soil moisture measurement system. Our goal is simple: to reduce human error, to save water, and most importantly, to increase the quality of our crop yields with a fully automated data-driven monitoring system.
To understand why this is a financial imperative for modern farms, look at the dual cost of guessing. Overwatering strips the soil matrix of vital oxygen, effectively drowning plant roots. This accelerates destructive root diseases, triggers severe nutrient leaching, and wastes costly water resources. Conversely, underwatering subjects the crop to severe hydraulic stress, stunting growth cycles, and directly diminishing overall crop yield. Our verdict is definitive. Plants absorb nutrients efficiently only when the exact right amount of moisture is delivered consistently. To eliminate this guesswork, we engineered a scalable, automated measurement framework. Our primary sensor uses electrical resistance to measure volumetric water content or VWC across a full 0% to 100% saturation scale, boasting a rapid 10 millisecond response time. The system is powered by an Arduino Mega 2506 microcontroller as its processing engine, pushing data directly to an I2C 16:2 LCD display for operators.
As the engineering manager, I ensure that every single data point processed by the system follows a rigid, reliable 5-step instrumentation pathway. Step 1 is the primary sensor. 2 electrodes detect changes in the soil resistance because water conducts electricity perfectly. Higher soil moisture results in lower electrical resistance. Step 2 is variable conversion. This sensor probe passes the resistor changes to an onboard driver module. This module acts as a voltage divider circuit, splitting a constant 5V input across a fixed 10 kΩ resistor and the variable resistance of the soil. It outputs a stable, measurable analog voltage governed by the standard voltage divider law. Step 3 is signal conditioning. The Arduino built-in 10-bit analog to digital converter translates this voltage into a digital integer ranging from 0 to 1023. Step 4 is the signal processing. The software architecture scales these integers into a human-readable 0% to 100% VWC range using the map function. Finally, step 5 is the signal display. The optimized percentage and corresponding system alerts are pushed via L2C communication to the LCD for live operator analysis. Before running physical hardware, virtual validation was mandatory to guarantee flawless deployment. We simulated our entire infrastructure within Tinkercad, mapping and cross-connecting communication lines according to strict schematic layouts. The hardware pin A0 was established for raw analog voltage transfers, while dedicated serial data and serial clock lines were wired for stable I2C data packet transfers. Within our software logic loop, we implemented strict automated boundary conditions. We added a constraint function to clamp our readings tightly between 0% and 100% to protect the microcontroller from overflow or scaling bugs. We then built conditional threshold loops to drive real-time operational alerts. Any value below 30% triggers a high priority soil is dry status, signaling an immediate need for irrigation. Values between 30 and 70 log a soil is good status, showing a perfectly optimized crop zone. Anything exceeding 70% generates a soil is wet safety warning, preventing dangerous root waterlogging.
As Member 5, I led the physical hardware integration and field testing execution to bridge the gap between simulation and the unpredictable dynamics of agriculture. Following our schematic, we synchronize our components on a field test bench using an Arduino Mega an I2C daughterboard display module, and a twin electrode resistive sensor with driver board.
As the quality control manager, high system accuracy and reliability are my ultimate metrics. Verifying industry sensors require comparing outputs against a certified standard reference. However, with the meaning VWC standard targets is extremely difficult without expensive lab instrumentations. To solve this, we engineer an innovative web-based calibration methodology using standard digital balance as our reference standard. Using the strict physical constant where 1 mm of pure water equals exactly 1 gram of mass, we mix precise volume of water into 50 gram sample of oven baked, complete dry soil at steady 20% interval. We plot errors against full scale span using standard industrial metrics. Here is the formula. To discover structural non-linearities, we took measurement along both an increasing moisture path and a decreasing path. Our data confirmed that while the sensor maintained a nominal full-scale accuracy of ±3%, our decreasing path unveiled a peak error of 5% at 40% VWC input. This divergence revealed a clear hysteresis effect. From an instrumentation standpoint, we successfully isolate the physical cause of this error. First, mechanical soil compactions and metric displacement from repeat probes insertion create microscopic air gaps around the electrodes. Second, capillary water retentions cause thin film of moisture to cling onto the exposed metal probes during removal, creating a lingering resistance measurement lag.
To rigorously validate system performance, we deploy our prototype across 3 distinct environmental samples simulating real agricultural scenarios. Sample A represented an unintegrated plot under severe drought stress. Sample B simulated a cultivated, optimally maintained garden soil root zone. Sample C simulated highly saturated, waterlogged lowland mud collected post-rain event. The system operated with remarkable speed and stability. In sample A, the dry soil's height resistance kept the voltage near the 5-watt ceiling, logging a high ADC reading of 910, which translated flawless to a 6% moisture display and an urgent soil is dry alert. Sample B achieved moderate electrical conductivity, dropping the raw ADC integer down to 730, generating a scale output of 51% and printing soil is good. Sample C water abundance maximized structural conductivity, driving the ADC integer down to 539, registering a 100% saturation warning of soil is wet. This live verification proved our multi-element pathway operates smoothly under changing environments.
While our primary resistive sensors is an exceptional educational framework for data pathway, it processes poor long-term durability for real commercial deployment. Exposed metal electrodes suffer from a rapid degradation due to accelerated electrolysis when direct current flow through wet soil. Furthermore, it has low chemical stability, meaning dissolved salt from fertilizer artificially distort soil conductivity, leading to massive calibration drift. Therefore, to scale this from a prototype to a high-yield commercial target, we analyzed an alternative industrial-grade capacitive sensors, the DF robot RS485. Instead of electrical current, it measures the soil dielectric permittivity. Its electrodes are completely insulated with waterproof IP68 exposé, making them entirely immune to soil wear, oxidation, and salinity spike.
Group 5 didn't just build a prototype, we built a foundation for a more reliable and a more predictive future design in commercial farming. And to bring our idea to the market, we will need to undergo 3 more phases. First, we will replace the resistive sensor with a capacitive sensor that is insulated with a waterproof epoxy. Next, by knowing if the soil is drying out or wetting up, we will rewrite the code so that the lag in response and hysteresis error due to capillary retention is removed entirely. Lastly, for the versatility of our system, we will incorporate more sensors, like the pH sensor or the temperature sensor, for more comprehensive analysis of the soil condition. That's all from Group 5. Thank you and have a nice day.